Yeah, comes on everyone. Let's start off. Hope everyone give it a try. Now, let's see how to do this thing. So we have three tuning forks oscillating at the same time. So let's start with this. Let the equations be y1 is equal to a sine kx minus 2 pi f minus 1t. Omega is 2 pi f now. So y2 is a sine kx minus 2 pi ft. Two pi f plus 1t. Now, first let's add. So y resultant let's add y1 plus y3 plus y2. So when you add 1 plus 3, again sin a plus sin b, you end up with 2a sin kx minus 2 pi ft cos 2 pi pi t cos a minus b, when you subtract that, plus the y2 equation would be a sin kx minus 2 pi ft. So from here, if you take out that thing common, you end up with 2 cos 2 pi t plus 1 amplitude sine kx minus 2 pi ft. So this is a progressive wave. And this whole term here is your amplitude. This is the amplitude which is changing with the time. Clear this? Now, if I try to plot a waveform for this, what do you see? So we have amplitude 2 cos 2 pi t plus 1 into a. You can clearly see this amplitude, this value, right? Cos ka value goes from minus 1 to plus 1. This value varies between cos 2 pi t will be between 1 to minus 1. That means amplitude ka value will vary between, when it is plus 1, it is 3. A to a. That's the maximum value, the minus 1. So the variation is going from plus a to minus a. Meaning if you try to plot this, it would look something like this. Again, amplitude, we are just taking the magnitude. So it would look something of this sort. So that is A. And the next one will go to 3A. So this is how the waveform would look. And you can clearly see here omega 2 pi t. Omega is 2 pi. Therefore, the time period is 2 pi by omega, which is 1. That means in 1 second, the cycle is going to continue every 1 second. So in 1 second, this is what happens. So we have an increase and then again increase. So this is amplitude A and this is 3. So if you try to hear this is how it would look like. It is like, meaning small intensity and big intensity. And we know intensity is proportional to the amplitude square. So we get 2 beats, and both of them have variable intensity. This 1:9. So the second sound will be 9 times more intense. So there is one time, right? I framed a question like this. They said there is a detector which can detect only intensity 4i. Getting it? And this 3 frequencies are sounding. So how many beats does the detector detect? It will not detect this thing. So it will only detect 1 beat per second. You're getting it? You can play around like that. We have an instrument which can measure only 4 times the intensity and greater. So this thing will not be detecting anything less than 4i. So this is there. So this is how you actually do it. But you can remember the general result for a mains or bits purpose, right? If you're tuning Fox frequency f minus n, f and f plus n are sounded together. We get 2n beats. You can just take the first one and the last one and subtract. Now, if it's a mains or a bits level question, they won't ask you intensity and all this stuff. Have a look at this. This is how you can play this out. That was the reason the bits बोल रहा हूँ. ये beats का derivation was important. Do have a look at this.
Sir, how did you get 1 second over there? वो नहीं समझा मुझे. Like 1 second में how
Cos
did you conclude कि a and 3 ये होगा?
this value will go from 0 to 2 pi na re God.
Yeah.
So what is the frequency of that? Omega कितना था? 2 pi था. Cos omega t. If
Okay.
omega is 2 pi, what is time period? 2 pi by omega. So what is
Hmm.
the
One
time period
second.
of that function? That function
One
repeats
second.
itself after every 1 second.
हम्म. वो भी तो समझा.
No, that means when that cos 2 pi t ka 2 pi t value goes from 0 to 2 pi, the cos ka value will go from -1 to +1, isn't it?
Yes, I got it.
This here is omega. All clear with this? Yes, that is how you do if you have multiple frequencies. So if they ask you about anything there, like like what is the intensity and all, it suddenly becomes an advanced question. But this was actually a mains question. F minus one, F and F plus one are sounded together. How many beats you will get? But that was the mains question. You just take F minus one and F plus one, and you're done. You get 2 beats. People think you get 4 beats. They think this is producing 1 beat, this is 1 beat, and this is 2 beats. So people get confused. There are 4 beats. You can't do that.
Sir, can we say that there are actually 4 beats, but the 3 beats are clubbed into one? So you get 3 over there.
We don't know. Re. हो सकता है. We can see. Once we know the answer, we can make any logic.
So,
अभी इसके लिए क्या करेंगे? What will you say the logic for this? भाई बोल रहा हूँ. Since we know the answer, we are setting it up. Yeah. Next one. So technically, with this, the chapter gets over. Getting it. After this, we have Doppler, which was actually removed from the mains portion. Doppler effect in sound and Doppler effect in light. Doppler effect in light was there only for mains. अभी पूरा डॉपलर ही निकाल दिया तो मेंस में इट इज नॉट देयर बट बिट्स में सीईटी में आल्सो आई डोंट थिंक इट इज देयर बिट्स में इट्स स्टिल देयर एंड एडवांस में द पोर्शन 2024 it was there. So this year when we get your new portion somewhere in October or something, then we will actually know advance में है या नहीं है. But just in case, we will still finish it off. It's not a bad topic, it's a good one. But there, so that is a risk we have to take. Instead of teaching you in the end, better we finish it off a bit now. So what's Doppler effect? So when there's a relative motion between the source and observer, the observer hears a frequency different from the source. Right? This phenomena is called Doppler effect. Now, let's take some cases. Case 1, let's say observer is at rest. And the source is moving. So, observer is standing here. We have a source here. This is sending waves. Frequency is f. Now, what do you mean by frequency f? So frequency f, so we get the time period t is equal to 1 by f. This is the time interval between two pulses. So if you say frequency is 10 hertz, meaning I'm sending a pulse every 1/10 of a second. This is the time interval between two consecutive pulses. C is the speed of sound. And let this guy go with the speed V source. Okay? So this is the scenario at t is equal to 0. The first sound pulse was released. This was your first pulse. Now, after time t, the capital T, the man is still here. The source must have traveled somewhere here. So the source must have traveled somewhere here, which is Vs into t. And this first pulse must have gone already here. This was your first pulse. And the second pulse was released here. And since this is traveling with speed of sound, the first pulse must have traveled a distance of c into t. So now, how do you define wavelength as? It's the distance between two troughs or two crusts. Now you're sending the two pulses with this. This distance here is called lambda apparent. So the observer will start thinking the distance between the waves is not lambda, but it is something else now. So we call this thing lambda apparent. The apparent wavelength. This is nothing but Ct minus Vst. So the observer thinks the wavelength has shrinked. Have a look at this. So that means whenever the source moves, he will feel the wavelength has decreased. And now if you try to use the formula F apparent, which is nothing but the speed of sound by lambda apparent, this would be C by C minus Vs into T. T is nothing but 1 by F. So we get Cf by C minus Vs into F. So this person actually hears the frequency is more. If you're sending a wave with 100 hertz, he will think it is maybe 110 hertz. This is happening because the waves are getting more clustered. He's sending it more close. Let me give you a more example. Listen to this thing. I'll get back to this. Let's use a mechanics example. You're at rest here. I'm standing here. Okay. Distance between us is 10 meters. I'm throwing stones on you. So I'm throwing chocolates on you. Getting it? Let's say I'm throwing stones. Let's say one every second. 1 stone per second. And I'm throwing with a speed of 10 meters per second. Getting it? I'm also at rest. So when I throw the first stone, when will this first stone reach you? Distance between this 10 meters per second, and let's say I'm throwing stones with 1 meter per second. When will the first stone reach you? So the first stone will travel. The first stone will reach him at t is equal to 10. The second stone will reach at 11, third stone 12, 13, 14, so on. So the first stone will reach you at 10, second stone will reach at 11, 12, 13, 14. So what will you think? Are sir is throwing stones at me and I'm getting one stone every second. Fair enough. Standard scenario. Now, same thing. Let's see what happens if I start walking and throwing at you. Let's say I'm walking with half meter per second. And again, I'm throwing stones with a speed of 1 meter per second. Now look at this, what happens. I throw the first stone. When will the first stone reach you? T is equal to 10. Fair enough. Now, between throwing the first stone and second stone, the time interval is 1 second. So in that 1 second, what will happen? I won't be standing here anymore. I will be throwing from here. I must have traveled 0.5 meter and this distance is 9.5 meter. So I throwed my second stone from here. How long will the second stone take to reach you? 9.5 seconds. Getting it? So that is after 1 second. So this stone will reach here after a time interval of 10.5 seconds. Is that making sense? The first stone is thrown at t is equal to 0. The second stone is thrown after t is equal to 1. I am throwing the stone at t is equal to 1. But you will take 9.5 seconds to reach the other person. So it is 1 plus 9.5. You will reach the other person at 10.5. Then I will throw the third stone. I will travel half meter more. So t is equal to 2 seconds. I'm already 1 meter from the initial position. I am throwing the third stone at t is equal to 2. So this third stone has to travel only 9 meters. Right? So that will reach in 9 seconds. So 9 plus 2, the third stone will reach at 11 seconds. Now, what will you think about this? You will think, Arey, this person is throwing stones on me every half second. But in reality, I'm still throwing stones every 1 second, isn't it? Are you getting this example? This is what is exactly happening with the waves. Even though I'm throwing 1 stone per second, because every time I'm getting closer, the stone has to travel lesser distance. It starts giving you a feeling as if there are more stones coming every second. Is this example making sense? If you ask me, this is the Doppler effect. This is what is happening when the source moves. Fair enough? Got the idea? So this is the same thing I showed here. Please have a look at this now. So not only with the sound waves, even when, a vehicle is moving and it is throwing something, it still works. That's because all the particles are not starting from the same position. That small difference in time interval will create that issue. It feels like you're throwing more stones. Even though if you say at any point of time throwing only 1 stone per second, but you receive stones at a much faster rate. Yeah. We will put on that all formulas together in the end, but next thing, what if the source is going away? I'll leave this example here. Case 2, the observer is still at rest, but this time the source is going away, Vs like this. This is t is equal to 0. This is your first pulse. So after some time t, the source must have traveled backward. This must be Vst. And this first pulse must have come somewhere here. This must have traveled a distance of Ct. And you're releasing the second pulse from here. Now the person thinks the distance has increased. Now your lambda apparent becomes C plus Vs into T. And F apparent would be the speed of sound by lambda apparent, which would be C by C plus Vs, and T is 1 by F. So in this scenario, the frequency decreases. So this is what happens whenever the source moves. It messes up the wavelength. When source moves, wavelength changes, and therefore the frequency changes. Clear? Next thing. What happens when the observer is moving now? Can I turn the page? Any doubts on this? I hope anyone is still confused with Doppler. I think that stone thing should have made things clear. Case 3. Observer is moving, source is at rest. We can combine everything later on all two cases. So this time, this guy is going with some V observer. The source is at rest. So it is generating pulses. So now there is no problem. The wavelength is same. This is coming with speed of sound. But the observer will think the rays are coming faster or the waves are coming faster. Observer feels relative velocity basically. Because he is running opposite to it, he will be reaching the waves faster. Speed of sound has become c plus v naught. This is your C apparent. So F apparent would be C apparent by lambda, which is C plus V naught, and lambda is nothing but C by F, so it goes up F. So here the reason is different. When you are running yourself, you think the sound is traveling faster. So here wavelength does not get affected, but the speed of sound gets messed up. Case 4, same thing. Observer is running away this time, V naught. And the source is sending the waves. Same idea here. So he will think the C apparent is C minus V naught. F apparent would be C minus V naught by C into F. So whenever the source moves, something happens. Whenever the observer moves, something happens. So when an observer moves, C apparent changes. So you have to be careful here. You should never use relative motion in Doppler effect. That is because when the observer moves, it is going to affect the numerator. When the source moves, it's affecting the denominator. So you can't say I will stop the observer and I'll do the problem if both are moving. So yeah, I'll make that as a statement. So now we are going to combine these two cases, observer and source when both move. Clear? Now, when I do all of them together, the observer moves, the source moves. This is your formula there. So there are 3 levels for this formula also. So let's see each one. All are same, but we'll take it one at a time. So C plus or minus V naught by C plus or minus Vs into F. Now, when to use plus, when to use minus. Now, this is not a concept as such. It is more of an intuitive thing. Just try to understand. If source moves towards the observer, what should happen? Frequency should increase. And where does the source there? Source is there in the denominator. Matlab, you need to understand, should I put a plus or minus sign? It's more of a doing it intuitively. Now, if observer moves towards the source, now understand, you really need not go, matlab, the distance need not decrease. Are you trying to go? Are you trying to go away? That's it. We are not actually interested whether you are getting close or not. Now, there are only 4 possibilities here. So we have the observer, we have the source. Now, first thing, the observer is going towards the source. The source is also going away from the observer. So ask yourself, what is the observer trying to do? He is trying to go towards the source. Now see, whether he's getting close or not, I don't care. He is trying to go towards. The frequency should increase, right? But where is observer velocity? In the numerator. How to increase? Plus or minus sign? Plus. Next thing, the source is going away from the observer. So frequency should decrease. But where is source ka velocity? Denominator. How to decrease this function? Plus. Are you getting how to use plus and when to use minus? Let me show you one more. Second case. This guy is coming this way. This guy is also coming this way. When source is also coming towards the observer, observer is also going towards the source. First thing, observer is in the numerator, source is in the denominator. Observer is trying to go towards the source. So frequency should increase. So numerator should be more. So means it should be plus. Denominator, the source is going towards the observer. So frequency should again increase, but source is in the denominator. Means denominator should be small. Minus. Is this logic making sense? So this way, if you think like this, there's no confusion when to use plus and when to use minus. So you're being a little more intuitive. It's not a concept as such. What about this guy? Now, this will give you a feeling A and D are same. A and D are not same. What about C? The observer is going away, so it should decrease. The source is also going away, it should decrease, but you're in the denominator, so plus. The observer is going away. The source is coming towards, so it should increase. Check it out. These are the 4 cases. Please have a look at this. Confused, please ask me when to take plus, when to use minus. You just need to ask yourself, if the source is coming towards me, it should increase, but the source ka velocity is in denominator. So make it small. How do you do that? By putting a negative sign.
So can you
If
have
the
B and C का denominator again?
look at the source now. What is the source doing? B part mein. It's going towards the observer or going away?
So going towards
Going towards. Should the frequency increase or decrease?
the increase
Increase. But where is the source ka velocity?
or in the denominator.
So if I want to increase this function, यहाँ पे क्या करना है? Plus रखना है, minus रखना है?
Minus.
That's it.
Okay.
Like I said, it's not a concept. Meaning this is how I remembered when it is plus and when it is minus. If you have something better, that is also fine. But all are clear when to use plus and when to use minus sign. No, this is not the complete formula. There is one more in this. But please have a look at this. The sign should be clear. Because you go for one minus sign, the whole thing will go for a toss. Next thing, the actual formula is this. F apparent. Suppose if there's a wind also blowing, C plus or minus wind plus or minus V observer by C plus or minus wind plus or minus V source into F. So here W is your wind speed. Remember, the speed of sound C ka formula, right, is derived with respect to the air. If air itself is moving, then the speed of sound actually increases. So in this again 2 cases, see what happens. Now if the observer is here, the source is here. Logic is simple. Ask yourself, the sound is traveling from the source to observer like this. Now there are 2 cases. Let's say the wind is blowing like this from the observer to source. So is the wind supporting the sound or opposing the sound? Opposing, so speed will decrease. Right? So the speed of sound will become C minus W. because c is the speed of sound with respect to the air. And if the wind itself is blowing, the speed of sound changes. If wind blows opposite to sound propagation, the formula becomes F apparent C minus W plus or minus V naught. So V naught, so we can do from the previous logic, plus or minus Vs into F. Same thing. Sound is going this way. And let's say your wind is also supporting the sound now. So wind is blowing this way. In this way, F apparent becomes C plus W plus or minus V naught. So V naught and Vs ka plus and minus is from the previous logic. There. This is your formula when the waves are traveling in one direction. There is one more variation, we'll see that, but this is the primary formula. With this thing, maximum number of questions do get over. Now, while using this formula, there are a few things which we need. Let's see that. You can copy down that formula, C plus or minus W plus or minus V naught. Clear? Now, while using the formula, few things you have to keep in mind. First thing, this formula is valid only when source, observer, and wind travel along the same direction. With constant velocities. If someone starts accelerating, this is gone. Second, this would be an important thing here. Never use relative motion. Meaning, don't say I will stop the observer with respect to ground, with respect to source, and I will try to study. It doesn't work. Never use relative motion to solve. Always solve in the ground frame. Meaning, you saw the reason was simple. Whenever observer is moving, it is affecting the numerator component. Source is moving, it is affecting wavelength. Observer is moving, it is affecting speed. Both the quantities are not affecting the same thing. That is V naught and Vs are always with respect to ground frame. So don't try to solve this from the source ka frame or observer ka frame. This final thing would be pretty interesting. F apparent is C plus or minus wind plus or minus V observer. Sometimes in the questionnaire they'll ask you find the lambda apparent. Meaning great, this is the apparent frequency, but what is the apparent wavelength? So you need not do everything there. It is there in this question only, in this part. C minus W plus or minus V naught by C plus or minus W plus or minus Vs. Bring that F down. So this is basically the C apparent, the numerator, by lambda apparent is the denominator. So if someone asks you find the wavelength, apparent wavelength, you just need to put that F down and you got your apparent wavelength. C plus or minus W plus or minus Vs by F. C apparent is C plus or minus wind plus or minus V naught. So that formula contains both C apparent and lambda apparent. There's no need to solve it separately. There, have a look at that. Let's see some problems on this. And then later on, we will see what happens if these things are not on the same line. Now, those questions will be all proper advanced only. Generally, mains level, they would have just stuck to here, but that got removed. So maybe bits level questions would be of this thing. Clear? Let's see a question. If you got this question, you understood the formula. So we have a bus here with a siren, frequency F. So here the vehicle itself is going with a speed of 10 meters per second. We have a person A here on the road. He is going with 5 meters per second. We have a person B here who is coming this way with 10 meters per second. We have a person C here. He is going towards the bus with 5 meters per second. No need to solve. Just write that plus or minus VC mina. Put the signs, plus sign, minus sign. If you got this, that is sufficient. Let's do one thing. Let's see, go this way backward with 5 meters per second. And there is one more person who's sitting inside the bus, chilling out, D. D is sitting in the bus. Let's make it more deadly. Wait. Let's say the siren is in the middle. It's a weird bus. This is going with 10 meters per second. We have D sitting here and E is sitting here in the front. D and D are inside the vehicle at rest. And in all this thing, we have wind is blowing this way. Let's say wind speed is another 5 meters per second. The speed of sound is 330 meters per second. The frequency F is 500 hertz. Now, I don't want you to simplify this. I just want you to write like this. Like, for example, if you look at A, C minus W plus VA by C minus W plus V source into F. Meaning, if you write like this, it is sufficient. Meaning, we can always substitute the values. So I want you to find F apparent, lambda apparent, and C apparent for A, B, C, D, E. There, like I said, you do this thing, you actually understood the formula.
So can you go to the previous page for a minute? Yes, okay.
I'll help you with one question, say. Listen, I'll show you for A. So the formula for F apparent, we are doing for A, okay? C, right? The formula plus or minus W plus or minus V observer by W plus or minus V source into F. So let's be first clear, who is the source, who is the observer? The vehicle is the source and the A is the observer. So C, how is the sound traveling here? Now for person A, the sound is traveling this way. Isn't it? The sound is traveling to the front. Now, how is the wind blowing? Wind is blowing backwards. So is the wind supporting or opposing? Opposing. So minus W. Next thing. A, what is A doing? A is going away from the source or towards the source. Now see, I don't care. I know, meaning this is 10 and this is 5. The bus is getting closer. I'm not interested in that. I'm only interested in what is A trying to do. A is trying to run away from the bus. So frequency should decrease. And it is in the numerator. So minus VA by C minus W. What is the bus trying to do? Bus is trying to go towards the source, observer. So frequency should increase. So minus Vs into F. Done. Substitute the values, you'll get the answer. F apparent. What is lambda apparent? If you bring that to the denominator, C minus W minus VA by C minus W minus VS by F. The numerator is C apparent. The denominator is lambda apparent. Understood how to do this? You just need to check for each one, the signs only. The main thing is the signs only. Then it is just a matter of substitution. Can you do for BCDE? Especially I'm interested for D and D. D and D would be good theoretical questions. What happens to the frequency heard by D? What happens to the frequency heard by E? What happens to the wavelength seen by D and wavelength seen by E? Advanced level also, they can ask you that as a more than one choice question as a statement question. But chalo, let's try, you will see. Let's try for BCD. No need to substitute the values, meaning once you got this, it is just a matter of putting there and solving.
So why is VS negative in this?
What is the source trying to do?
It's pushing it towards A, right?
So frequency should?
Oh, yeah, sorry. Yeah.
Frequency should increase, and it is the denominator. So denominator should be small.
Yeah.
Make the bus soundproof items. Let's try. Try get it for the B. See whether you got the B clear right. So F apparent, now the sound is going forward, wind is going opposite. So C minus W. B is running towards the source, matlab frequency will increase. So that is VB plus C minus W. The source is going towards B, so frequency should increase, but you're in the denominator, so minus VS into F. So bring it down, so you'll get C minus W plus VB by C minus W minus VS by F. Numerator is C apparent, denominator is lambda apparent. Check. Same thing if I do for C. Now C ke liye what is happening? Sound is going this way. Sound goes backward. That would be C. The wind will support, and the C guy is trying to run away from the source. Now again I'm saying I don't care whether you're getting close or not. Right? So wind is, you should not see that. You should see wind is just helping the sound or opposing the sound. I don't care about the speed of B. When the sound is going this way, wind is which way? Backward, right? It is pushing the sound backward. So opposing the wind ka speed, sound ka speed. So this is C plus W minus VC by C plus W. The source is also going away, so it should increase plus VS into F. Please have a look at this. Like I said, the main thing is that plus and minus signs. If you got the sign, it's over. You mess up one sign, the whole thing will go for a toss. There, ABC is standard. Now let's see about D and D. Now again, you need to understand, just because I'm sitting in the vehicle doesn't mean anything. You treat the man independent of the bus. Meaning D and D are traveling at 10 meters per second right side.
Sir, is the wind affecting the scene inside the bus?
Yeah. Wind is affecting.
How will we know this in the exam?
There is a window there. People will die if you put them in a sealed bus.
Okay.
There is a window there. So, I'm not a big artist, but we'll put a window there and D is hanging outside like this. Happy. Flying like something like this. So. It's like this thing. The sound is coming from outside to him. Getting it? Don't think like the sound is coming from inside. The frequent thing is outside. Right, Lakshika? Aryan, you go top. So you know what they'll ask in this question for D and D? They'll ask like this. The frequency heard by D is F, and the frequency heard by E is F. The wavelength seen by D and D is also lambda. And the explanation they'll give is this. Since the relative motion is zero between the bus and the observer, the frequency and the wavelength remain same. Take a minute, I'll show you this thing. It's a good one. Now you just treat this person D and D as two independent people. You're getting it? D is here. He's also going with 10 meter per second. E is also here. He's going with 10 meter per second. Now, when you try to write for D, see, now the sound is coming backward, right? Lambda and C will get messed up. Sound is coming backward. So, and the sound is also coming back. Wind is also coming back. So for D, the sound actually is being supported by the wind. And this guy is going towards the source. Getting it? The frequency is in the middle, the source. You're trying to go towards, so frequency should increase. So that is VD by C plus W. Now the source is trying to go away. Now see, again, I'm saying it is trying to go away. Technically speaking, distance will never change. I don't care about that. I'm not actually interested whether the distance is increasing or decreasing. I'm interested, what are you trying to do? You're trying to go away. The frequency should decrease. So this is V source into F. But here VD is equal to VS. You're getting it? Therefore, F apparent will come out to be F. He will hear the same frequency, but if you look at this thing, the lambda is not the same. The reason why he's hearing the same frequency is not because relative velocity is zero. If you look at here, the wavelength has actually increased. Lambda apparent is greater than lambda. C apparent is also greater than speed of sound. But the ratio is remaining constant. So the person D will think frequency is same, but wavelength increased. So if you write a reason like this thing, right? Since relative motion is zero, frequency frequency remains same. This is a blunder. This is a bullshit statement. Relative velocity has nothing to do with this thing. So, but generally people think that when kabhi kya lagta hai na, lambda also will remain same. This would be a pretty good question. The wavelength increases even at an advanced level, because most people only think about F apparent. They don't realize about C apparent. The same thing, if you try to do for point E, this person E, you will observe the same thing here, F apparent. This guy would be C, the wind is opposing him, minus W. He is also trying to go away. So minus VE by C minus W, this is minus V source into F. This again comes out to be F only, because VE is equal to VS. And you can clearly see here, lambda apparent is C minus V minus VS by F. Lambda apparent is less than lambda. Lambda decreases. The two people in the bus will think, one guy will think wavelength is more and one guy think wavelength is less. This would be a theoretical question in the exam.
Sir, will there be any difference between what D and E hear? Like
Come
just with
again?
their ears, if they're just hearing the sound, will there be?
They will hear the same frequency. Frequency से कुछ difference नहीं पता चलेगा उनका. But only when you try to somehow measure the wavelength, they will realize like it is not the same.
Okay, so we can hear only frequency and all the change in wavelength.
We can't detect wavelengths. We detect only frequencies.
Okay, so
All clear with this?
So why is it minus V over there? Can you explain again?
इसमें
हाँ
what is this guy trying to do? Going away from the freak source, ना?
हाँ
तो frequency क्या होना चाहिए?
हाँ minus.
Decrease. So minus. This is called a ripple tank. So what is happening there now? So you have a glass plate. They kept some water on the glass plate, and they kept a small tip, like a needle or something, and that is on the water surface. So when it is vibrating on the left side, you can see that handle is vibrating up and down. So this thing is continuously poking the water. So this is what you will see. Let me show you how it looks. So, and they kept a light at the bottom, so that light rays passing through the glass, and you can see the reflection on the top there. Can you see what is happening? So when you're hitting the water non-stop continuously, you can see that ripples. And they have a small camera also that projects onto the screen there. That's what is actually happening on the water surface. So there. So that thing is oscillating, let's say 10 times per second. So it is generating 10 times that circles per every second. So 10 waves per second. This is a 2D wave, getting it? So actually the amplitude drops. We will see that in wave optics, but you can see the waves. So the frequency and wavelength are inversely proportional to this thing. So speed of sound is equal to f into lambda. So in a given medium, speed is constant. So see what happens. Now here the wavelength is the distance between two circles. Now he's decreasing the frequency. He's slowing down. Can you see the wavelength has increased? The distance between two pulses have become bigger. Now if I increase the frequency, can you see the distance becomes smaller? They're more closer now. Again, see that thing here. Now just choose any two things. Can you see the distance is big? This is the low frequency, high wavelength. Now when I increase the frequency, same thing. Now if you look at it, can you see the distance is smaller than the previous one? This is a high frequency, low wavelength. And then you can clearly see it is becoming much smaller. And the distance between that each ripple is a wavelength. Now you're trying to move the source. Now this is Doppler effect. Now see, when you're moving the source, what happens? The people in front of you will think waves are getting compressed. People behind you think wavelength will decrease. That's what I showed you in case 1 and case 2. Now see that in slow motion. So when he's traveling, can you see? The waves in the front are closer, the waves behind are bigger. The wavelength in the front is increasing, wavelength behind is decreasing. So this is what I was saying. If there is an observer in the front, he will think the wavelength is less, so frequency is more. If there's an observer behind, he will think wavelength is more and the frequency is less. Now see if you go, now wavelength is more on the upside and wavelength is less on the downside. You can clearly see here, the waves on the top are much bigger, whereas the waves at the bottom are compressed. Did you see? They're more tightly packed. So this is what I was saying. Whenever the source moves, what happens is a change in wavelength. But this is what we call as Doppler effect. Now, if you go fast, then you can clearly see even more. Can you see how much it's getting distorted? So if the source goes pretty fast, the frequency ka change will be much higher. And if you go faster than the speed of the wave, I think here you can see more clearly. You can see the cluster. The waves got fully packed in the front and the upper part as the waves got spread out. And if you go faster, we get a shock wave. There. This is called a shock wave. Basically, if your source goes faster than the speed of sound, means what will happen? The first wave is come out, you're traveling faster than the wave, the second wave overlaps with the first wave, third wave overlaps with the first wave, and so on. All the waves will, form an envelope in front of the vehicle normally. And what we get is a sonic boom. So it's called a shock wave. There. These are two sources, coherent sources and all. This is a wave optics experiment after this, fringe widths and all. We will see that thing again later on. So I'll be posting this anyway. So if wave optics is done, you can watch it. You will actually understand what is happening. That is one. I hope now the Doppler part is a little better. You understood actually what is happening with the waves cluster there. Do we have that? One sec, let me see. Do I have one more simulation? No, I don't have actually. Doppler का simulation नहीं है इनके पास. I think maybe I should fund this PhD people. Let's see. So be careful with that statement. Huh? So because the relative motion is zero, frequency remains same is a blunder. That has nothing to do with the same. They have velocity, so wavelength changes, C apparent changes, and that's why this thing is remaining same. Is this clear, everyone? So even if you're sitting in the same vehicle, even if you go with the same speed, lambda gets affected. So idea is simple, Ray. If this is your source, and if the source is going this way, the waves in the front will get clustered, the waves at the back will get spread out. I don't care where, what is the observer doing. Let the observer run left, right, let the observer dance here, it doesn't matter. Wavelength depends only on the source ka velocity. Is that clear? That's it. So wavelength has nothing to do with the observer ka velocity. Any doubts on D and D part, please ask me. That would be a pretty good question. Let's see one more. So we have a wall here. We have a frequency F. The vehicle is traveling with V, and let's say the wall itself is traveling with 2V. C is the speed of sound. And there's a observer inside. So the first question, find the frequency and wavelength heard by the wall or seen by the wall. Find the frequency of the echo, right? Find the frequency and wavelength of the echo heard by the driver. So after hitting the wall, the sound will come back, na? And find the number of beats heard by the driver. So the driver is going to hear two different frequencies. So there'll be beats. Let's get this. So just to give an idea, initially the sound is coming here. So this is the source, wall is the observer. After sound hits the wall, the sound will start reflecting. Now the wall is the source and the car is the observer. So they will exchange places. Okay. Try. Reflected speed. What do you mean by that? Speed of sound does not depend on the source. It depends on the medium. It doesn't mean if you run and start shouting, the sound will travel faster. Sound ka speed gets affected only due to the wind speed. Here, there's no wind. Okay. Try. Get all of them. I'll give you 2 minutes and I'll show you the whole thing. There's nothing there. It's just the formula. Source, observer, the sign convention. If you got this, put it in the formula, you'll get the answers. In that sense, Doppler is really not tough. Hey, don't do collisions for sound wave, right? So you're saying quotient to restitution for sound wave. You'll consider momentum for sound wave. Sound wave is a disturbance in the medium. It is not a particle moving on its own. Let's see the first part. So this guy, so always important thing, define who is your source and who is the observer. This is V, this is F, and the wall is the observer. So the F apparent F1, let's call it C, wind is not there. The source, first is the numerator is observer. Observer is trying to come towards you. So plus 2V. The source is also trying to come towards you. So C minus V into F. And lambda apparent will be C minus V by F. So whenever the sound gets reflected, the echo has the same frequency F1, and the wall behaves like a source. Whose frequency is F1. Now the second part of the question. Now the sound is coming from here. Whose frequency is F1? This is my source. This guy is coming with V, and this guy is my observer, the driver in the car. Now, if you ask him, what do you hear? He will say, okay, I hear F2, which is C. Now, the observer is going towards the source, so numerator may will get plus. So be careful with that. The denominator, the source is also coming towards you. So that will be C minus 2V into F1. Now, don't simplify this. Lambda apparent is C minus 2V by F1. Lambda apparent comes from here only directly. Now, what some people do by mistake now, they'll substitute F1 ka value here, then they will try to take the denominator. Don't do that. That will be a goof up. This is your lambda apparent heard by the observer. Now try to simplify this. C plus V by C minus 2V. F1 is nothing but C plus 2V by C minus V into F. This is the frequency heard by the driver, the echo. Now the driver hears two frequencies. Driver hears F, the sound which is directly coming from the siren, and he will hear F2. The driver doesn't know what is F1. I hope that is clear. The F1 only, he will think it is F2. So the driver, when he is driving, he will hear two sounds. One sound directly coming from the siren. Second sound is coming after the echo. So number of beats will be F2 minus F. Take them and subtract and you can finish it off. I will leave the working to you. So C plus V, C plus 2V by C minus V, C minus 2V minus 1 into F. That is your number of beats. I don't think you will get something. You can simplify that, but you can leave it there. Is this making sense, everyone? So whenever you want to find lambda apparent, whatever you hear, uska C minus 2V by F1 directly. Don't simplify it. If you want lambda apparent, don't simplify it. Number of beats is 3, kya? I don't think so you'll get such a good answer, but maybe. I'm not getting a feeling it will be 3. Is this clear, everyone? Easy? Understood? That's what I'm saying. Simple. Be very clear. Step 1, who is the source? Who is the observer? Step 2, sign convention. Done. You'll get the answers. So technically, Doppler, there's nothing there. This is the thing which I really liked about it. It's a good concept, easy to solve. Nice marks. Unnecessarily they removed it. But can't do anything. There are some good things also. They removed that entire transistors. I'm really happy about that. But that was hopeless. Clear? Next one. I hope everyone is getting the main thing, the sign convention and stuff. Let's see one more. We have an observer here who is moving with speed v. So there is a water here, maybe a pool or something. Inside the pool, there is a source of frequency which is going down with v by 2. And this liquid which is there, the liquid is rising v by 2. The water level increases at a rate of v by 2. Water level rises with speed v by 2. The speed of sound in air is c. The speed of sound in water is 4c. So the source is in water, observer is in air. Now we are messing up the mediums. So find the F apparent heard by the observer. What frequency will he hear? Now you can't apply the formula directly because the medium has to be same. How do you approach this? The hint is that only. You can't apply the formula when you have medium changing. So what you do? Let the surface be the observer. So apply the Doppler between the source and the surface. But the surface will behave like a new source which is sending the sound out. Now this will be the source and this guy will be the observer. So you split the problem into two parts. Basically, the interface will act like a wall. So do Doppler between the interface and the source. Then the source will, the interface will hear some frequency. Whatever it hears, it will send that only outside. Now the interface becomes a new source with frequency, which is sending waves outside. C plus V, 8C minus V. Can't you bring the man down to the फर्क नहीं पड़ेगा ना आर्यन इसमें. Tell me, in Doppler में did it really matter what were the distances between them? Distances never matter. You want to keep him here, keep him. Na, big deal. You want to put him inside the water and kill him. Now that's a different story. Don't. You're not that violent yet. Just because you don't want to do the problem, you can't go and kill people. You still have some humanity left. So first this will be the observer. Let this be hearing F1. So F1, now be careful, the formula C ka placement at the speed of sound. So C is the speed of sound in water, right? Minus, now the observer is moving away, so minus V by 2 by C water. The source is also going away from you. So it should decrease, so that is plus V by 2 into F. That's basically 4C minus V by 2, 4C plus V by 2 into F. This is what the interface will hear. And now the interface will start sending sound waves with F1. So this guy would be the source. And the man will hear F2. So F2 will be the speed of sound in air. So C is the sound in air. Now the observer is coming towards you. So plus V. This guy is also coming towards you, the source. So minus V by 2 into F1. So yeah, you're done. Substitute and you get the answer. So this will be C plus V by C minus V by 2. I will leave it here. You can put F1 there, you'll get the answer. Is this clear, everyone? That's it. You just treat the interface. If the medium is changing, you solve the problem in two parts. Frequency heard by the interface and the frequency given by the interface. So do it for water separately, do it for air separately. Only thing that will change, C ka place mein, it will get 4C. So this and that Volca problem kind of have same similarities. All clear with this? Any doubts on this? Neil, clear? Maulika? Got this? Udayan? Sure? Yeah. Adrit? Ali? Anika? Anusha? Arjun? Got this?
So in this case, although you still have to solve in two parts, you can like think of the water as wind only and apply
water, wind nahi hai, God. Water is not wind.
No, but like you can, it'll still work out if you use the normal formula only.
No. Try and see.
Okay.
See, here water level is rising, meaning this part is increasing. This water is not moving here. What you are assuming is this whole water is moving with V by 2.
Oh, okay, yeah, right.
Only the surface ka water level is rising, na? Maybe someone is pouring water here and this level is rising.
Yeah, understood.
Yeah. There we touched 50. Then let's see one more. Let's say we have a car with a siren frequency F accelerating with A initially at rest. Constant acceleration. Now, this is difficult to solve normally, but we will make it a simpler version of this question. Observer is at rest. So find the frequency. So the siren is on, the car started, both at the same time. Find the frequency of the first sound the observer hears. Now you can't use that formula. You have to go back to the derivation. So you started the vehicle with the siren, 0 speed, acceleration is, siren started at the same time. So that sound will come and reach him. So he will hear a frequency. That means the second sound ka frequency will be different. Third sound ka frequency will be different. The frequency is continuously changing now because the speed is changing, obviously. So I don't want all that. I just want the frequency heard by the observer for the first time.
So in this question, won't we need the distance between the car and the observer initially?
Let's assume this thing doesn't hit him and kill him, Ray. It's far.
Even then, sir. We
You
won't
don't
need it.
need Ray. You don't
Can
need
have to
it.
tell.
See the speed of sound. Why were you just so obsessed about killing the observer today? उसको तो पानी में डुबाना था, तुझे कार से मारना था, हाँ, नहीं तो बस में उसका साउंड प्रूफ करके kill him without oxygen. Happens. Happens when you study too much. Sometimes you do get violent. Even I was trying to destroy the Earth in 10 different ways after that surface tension experiment gone wrong. Remember that Kepler reaction ka thing? I was trying to build the world's biggest power plant. How do we do this? Go back to the derivation. Meaning, what was the derivation? Look at the case 1 ka derivation. I found the distance between the first and the second pulse. So what will change in this? This will change here. It will not be VST. It will be something else now. Right, I'll give you a minute. T0. This was your first pulse. After time t, you traveled a distance of half AT square. And here you released your second pulse. But in this process, the first pulse has already gone ahead. This distance was C into T, meaning this was your lambda apparent. So lambda apparent would be CT minus half AT square. And T is what? 1 by F. So F apparent would be C by lambda apparent. That will be C by F minus A by 2F square. This is the first frequency. You want to do the second, then you have to be to the distance between second and third, and so on. Clear? Easy? So you have to go back to the derivation there.
So what will happen like when one overtakes the other?
Which one overtakes the other?
Like one pulse can overtake the other, right?
Then in that case, actually overtake kabhi nahi hoga. If the vehicle starts going faster here, the pulses will start overlapping at the same place. They will drag each
okay.
other out.
Right.
So the pulses will start overlapping. Then we will get that stationary tips. You know that A plus A amplitude will keep bumping up.
Okay.
What we get is a shock wave. We don't have that in the portion, and it doesn't obey all these things. That becomes very destructive. That's what we call as a sonic boom. Okay, take a break. Come back by 7:2. Now we will see next after this what happens if this source and observer goes at an angles. Any doubt so far? Okay, take a break. Come back in 10 minutes. Camps on everyone. Next thing, what if the observer and the source are moving at angles? So let's say we have the observer here at t0, and let's say this guy is going with v0. And let's say we have the source here, frequency f, this guy is going with vs. This is the t is equal to 0. Now, the important thing here is the formula is still fine. The problem is, tell me one thing, when this sound is coming here, do you think you will hear this sound? By the time the sound travels from here to here, this observer must have gone from here to here. Isn't it? So the problem is the sound which was released at t is equal to 0, he can't hear at that point. So this sound must be traveling somewhere like this. And when the observer comes here, at some time t, that is when he hears the sound. You're getting it? And during that same time t, the source must have gone somewhere here, which I don't care now. What is happening with the b, it is useless. So if I name these points, let's call this point as b, let's call this point as b dash. And if you call this point as a, and if you call this point as a dash, so what you're actually interested is the line a dash b. Let's say this is theta 1 and theta 2. Maybe the lines are not parallel. Maybe I'll do it like that. So then the formula becomes, the formula is still valid. F apparent is C plus or minus wind plus or minus V observer by C plus or minus wind plus or minus V source. The only difference is all velocities have to be taken components along the A dash B line. So the wind speed, V naught and Vs are components. Along the line joining the source. So this is the thing here, see. Line joining the source when sound is released. So source is important when it is releasing the sound. That is point B. And observer when sound is received. So observer ka position is important when he is receiving the sound. That is A dash. So we are talking about the line AB, A dash B. So all components must be taken along the line A dash B. It's not AB. So your initial position of the observer is useless. Your final position of the source is useless. Is this making sense? So because this sound which was coming here, when it comes here, he is not there only. He's gone ahead anyway. That is the catch. So if you're moving at angles, this is what you have to take care. So components would be, this will be V naught cos theta 1, this will be Vs cos theta 2. If the wind is going this way, then W cos theta 1, theta 2, whatever it is. So in that sense, you have to take the components. Do have a look at this. So this would be the final version of the Doppler-Fedka formula. So the velocity component, you should take velocities along the line joining the source and the observer. Source should be at t0 and the observer when he's receiving the sound. Clear with this? Any doubts on this? Let's see a question. We have an observer here at the origin. is at rest. At a certain height, we have a source of frequency f. It is traveling from minus infinity to plus infinity. At a height. Okay. Here the observer is at rest. So I can ask you plot f apparent heard by this observer versus the x coordinate of the source when the sound is released. So the sound released at x coordinate, at a particular x coordinate, what was the f apparent of this thing? X coordinate of the source. Meaning, if the source is here, what is the f apparent? Here, what is the f apparent? I want a graph, f versus x graph. That's a good question. Let's give it a try. Options could be like this also. The frequency increases and decreases, frequency decreases and increases, frequency always increases, frequency always decreases. That's why I can put 4 questions also. But let's plot the graph. I think plotting the graph would give you everything. Approximately plot the graph. Exactly, we can't. Again, understand, we don't care about the distances. We are only interested in the velocity components. Decreases and then increases. Okay. Try. I'll give you a minute more. Decreases and increases. Okay. Increases and then decreases. Let's see. Now, when you're pretty far, right, when you're at infinity, if you actually think about it, it would look like this. When you're at infinity, you're like this. The velocity is almost parallel, isn't it? So at any instant here, if you look at this angle, this is theta. So at x is equal to minus infinity, this theta will tend to be 0. That means this velocity which you are going with v, you are interested in this component v cos theta. That means the frequency generated, right? This is Shansi, what he's doing. This frequency generated at minus infinity, right, will be what? The velocity is completely towards it. Getting it? So that means the component of velocity would be v only. The component along the line, meaning let's call it S and the observer. Is V. That means he is going to hear the maximum frequency here. So F max, so the frequency heard for this thing will be C. The source is moving, so C minus V into F. So when you're coming from minus infinity to origin, you can clearly see the velocity ka V component V cos theta is decreasing. So when this thing comes here, the velocity is V here. At this point, the V cos theta component is 0. Meaning at this point, he will hear the same frequency, F apparent only, is equal to F. And when you go to plus infinity, it extends to plus infinity. Again, theta becomes 0, but this time the velocity is, now look at here, this thing is going away from the source. So here you will hear F minimum, which is C by C plus V into F. Are you getting it? On the left-hand side, the velocity is towards you. Agreed. So frequency is greater than F, but it is decreasing. On the right side, the velocity is away from you. So frequency is less than F, and it is decreasing further. So if I try to plot this graph, X versus frequency. This is your standard frequency F. This is your F max, which is C by C minus V into F. This is your F minimum, which is C by C plus V into F. So at plus and minus infinity, your frequency started from here. It decreased to F apparent is equal to F, and then it continued decreasing. The graph always decreased. You started at maximum at minus infinity, then you reached minimum at the right infinity. So if you see, frequency always decreases. Because on the left-hand side, the velocity is towards, but it is decreasing. On the right side, the velocity is away, but it is increasing. So it is reducing more and more. This is how the graph would look approximately. Is this clear, everyone? So at this point here, the F apparent would be F. So exactly when you're on top of that, that sound ka F apparent would be F only. There is no change in frequency. So the answer is frequency always decreases. Please have a look at this. It will be an upward curve or downward curve. That is there. I'm just guessing approximately. You're saying like this. Because I feel if you draw like this, won't it just blow off to infinity like this? Shouldn't the graph be tapered off infinity में flattish? So I think it should be like this, but is there any mathematical way to figure it out? Because infinity pe, right, the graph should get closer and closer to this thing. So I'm not sure how will we, like this you're saying, because this gives me a pretty weird feeling, because if you say it is going like this and becoming like this, the slope is increasing and the slope is decreasing. So I'm not sure whether that would work. Yeah, meaning if you ask, I'm just trying to guess. Because मेरा वो logic था, if you say it is like this, I'll assume it is just going off to infinity. But I know mathematically maybe you can figure out something. Because see, this formula would be like this. F at any time would be C by F apparent would be C by C minus V cos theta into F. So this V cos theta here is decreasing. So maybe from there, if you can figure out, differentiate it and get the slope and check whether the slope is increasing or decreasing. Clear? Next one. Top view. We have a source here, which is going in a circle with speed u. from the center, we have a person standing here, observer at rest. This distance is r. Radius of the circle is also r. So this thing is going in a circle. Source goes in a circle with speed v. Now, so find the time interval between the maximum and the minimum frequency. Find time interval between. So when this is going in a circle, the frequency will change. So he'll hear a maximum and a minimum frequency. Neglect, the time taken for sound to travel. In this case, it shouldn't be a problem, but let's just take care of it. Because when sound is released and when it reaches, there's a delay. Sound to reach observer. So we are assuming the moment sound is released, immediately is hearing it. We are neglecting it. No, it's not higher. C is the speed of sound. Just need to figure out when you will get the maximum and the minimum frequency. See, the most common mistake now, what people think is this. They think you get maximum here and somewhere here. Now you need to understand at this point, velocity is this way. You are not interested in the velocity. You are interested in, now look at this thing, the component. So you tell me, when will the component be maximum? So the velocity of the source ka component along the line joining must be maximum. That is when it becomes a tangent. It's not the topmost point. When the source is going like this, the component of velocity along the line joining is maximum at this point, isn't it? So if you drop this thing here, that distance is 2r and r, this angle is 60 degrees. So at this position, the velocity component is going away. This is the maximum component. If you take the topmost point, the component would be less than v. So at this point, this person is going to hear a minimum frequency. This would be c by c minus v into f. Similarly, if you take the another tangent, at this point here, this is the velocity is maximum towards the observer. At this point, he is going to hear maximum, which is c by c plus v into f. Exactly when he's here, at this point, he's going to hear f apparent is f only. Again, here, again, he'll hear f apparent as f only. So there are 2 points where he will hear the same frequency. At 60 degrees from the top and 60 degrees at the bottom, you'll hear maximum and minimum. It is not the top and the bottommost point. What you're interested is the velocity components along the line joining. Now you have to be careful. There's a trap in the question. I said minimum to maximum. Now, interestingly, in this question, when you go from minimum to maximum, this is the time. But if I ask you maximum to minimum, it is this time. Both are different. So I could have framed a question like that. Find the ratio of time taken from minimum to maximum and maximum to minimum. Or you could say approximately plot the graph. So if I approximately plot the graph, this is how it would have looked. So if you try to plot f versus the time, this is f max. This is f. First of all, the heights won't be equal, f minimum. So initially your frequency is f, and then you're going to minimum. We'll go something like this. Again, approximate graph. And this time will occur at, what is this in 60 degrees now? 60 is how much? Pi r u by 3, pi r by 3u. So at pi r u by 3, you reach minimum. Then from there, again, I'm not drawing it properly. You reach again f ka value. Means you have completed half revolution, pi r by u. Then from here, you will go to maximum. This graph will be pretty unsymmetrical. How much did you complete? You completed almost 5/6 of the revolution. So this would be 5 pi r by 3u. And then you come down again. You come back to 2 pi r by u. So the graph would something kind of look like this. It's not a sine graph. It will be unequal lengths and unequal heights. And this would repeat. The frequency would be like this. This is your minimum. This is your maximum. So the time interval between maximum and minimum maximum is different. So you have to be careful what is being asked. Minimum to maximum. You should take 240 degrees. No, 240 degrees. 4 pi r by 3u. Clear with this? Next one. So x and y axis. We have the source here, frequency f, traveling with speed u, and this thing is d comma 0. We have the observer here. This guy is also going with speed u. Coordinates are 0 comma d. This is the scenario t is equal to 0. Find the apparent frequency heard by the observer when source is at the origin. Bas. That's the question. उल्टा हो गया ना? What did I do? Reverse किया? I wrote wrong. ये plus था. ये minus था. Yeah, my mistake. Let's get this. This looks pretty innocent, huh? It is serial killer, let's say. First option will be F. Let me ask you the question in another way. Then you'll understand what I'm asking. Listen to this thing. Huh? What is the question I'm asking you right now? This is the thing. Find the apparent frequency heard by the observer when the source is at the origin. Okay, ये question था. Now let me ask you another question. Find the apparent frequency heard by the observer due to the sound released at the origin. Both are completely two different questions. So you tell me, when the source comes here, do you think he will hear this sound? Question is, find the frequency heard by the observer when the source is at the origin. That means the source must have released the sound somewhere here. As the sound is traveling from here to here, the source must have reached here. समझ में आया? The person didn't hear the sound which was released at the origin. That sound was released before only. In the meantime, it took the sound to go from that point, we don't know which point is that, to the observer. This thing source reached from that point to the origin. Means you're supposed to take this angle, isn't it? You should take velocities along the line joining the source when the sound is released and the observer when the sound is received. Is this making sense now? So that thing was completely different. If I ask you find the frequency heard by the observer due to the sound released at the origin, then the answer is F. But this is something else completely. Most people will think that is a question and solve. So be careful. Try. I'll give you 2 minutes. That was a catch in the question. The sound was not released at the origin. Sound was released before. So if I have to draw the picture, it looks like this. This was T0. This is T1. This is T2. So sound was released here. The sound released at T1 is heard by observer at T2. So this guy here at T0. Now I don't care about T1 anyway, so directly we'll go for T2. T1 will be somewhere in the middle. Maybe I'll put it down. So we are interested in the point where the sound is released and the point where he receives the sound. We are interested in this sound wave, meaning we are interested in this angle theta. C by √2. Now, God, who told you that angle is 45? You made an assumption that is 45. That is not 45. How do you know that is 45? This is what is happening in the question. I hope the diagram was clear. So this guy is going with u. So this component is u cos theta. This guy is going also with u. If that is theta, this angle is 90 minus theta. So F apparent is C source, the source observer. The observer is going away and the component of velocity is going away to minus u cos 90 minus theta by the source is coming towards you. So the frequency should increase minus u cos theta into F. So this is Cu minus sine theta by cu minus cos theta into f. Now we are stuck with theta. If I know theta, my job's done. How do I find theta? So this, I think few years back, I tried solving it. Normally you can solve T1, T2, aa jayega answer. Then one of your senior told me, sir, if you just want theta and you don't want anything else, there's a much faster way. He just told me in one step, and I was like, shit, right? You can get this in 1 or 2 steps. Mein theta aa jayega. D, E, sub nonsense. You don't need anything. Take a minute, think about it. But I hope first this thing is clear. The source is going away, so component is u cos 90 minus theta. So I should take this component here, u sin theta. This component is going towards, so this component is u cos theta. Now this is the line you're interested in, right? Now from here to here, what is the distance traveled? You're traveling with speed u, and what is the time? T2 minus T1, agreed? So from this point to that point, the car is taking time T2 minus T1 into u. Fair enough. This distance is what? Meaning the same time, the sound is also traveling from here to here with a speed c into T2 minus T1. Do you agree? The length of the black line is speed of sound into time. The length of the red line is also the speed of the vehicle into time. And if that angle is theta, cos theta would be u by c. I don't need T1, I don't need T2. What I want is a ratio. The time taken for the sound to go from here to here should be equal to the time taken to go the vehicle to go from here to here. Both of them have same times. So that will be u into the time interval, and that will be c into the time interval. So cos theta will be u by c. Is that making sense, everyone? एक बार cos theta आ गया, sin theta भी आ जाएगा. Root over 1 minus u square by c square. Take that, substitute, you got the answer. Why do we take the sound released after time t1? We are not taking, we are taking the sound released at t1. You're getting it, Aryan? Question kya tha? Find the frequency heard by the observer when the source is at the origin. The source will reach the origin at t2. But I'm not going to hear that sound. That's what I'm asking. Why t0? You tell me. If you're going to say t0, then you prove that t1 is 0, no? You prove t1 is 0. I am taking the time could be anywhere between 0 to t2. Are you getting my point? I took a variable. You tell me, if t1 is 0 means what? You are assuming u is equal to c, isn't it? Means you are saying the speed of the vehicle is equal to speed of sound. Who told you that? You're getting it? Yeah. So it depends on the speed of the vehicle. Is this clear, everyone? This is a question where it is a difficult to figure out but easy to solve. This is a tough question. Even though the question looks pretty innocent, right? It's a tough one. Maybe here, maybe it looks like 4 or 5 steps, but idea click nahi hoga. And even I used to do this 4 or 5 years back. I literally used to find T2, T1 and used to get theta. Then this kid told me very nicely. I said, sir, do you really want T1, T2? I said, no, I just wanted theta. Then I said, sir, why don't we just cancel them? And then he told me this. I said, like, right, shit. Why am I calculating even T2 and T1? I don't need those. You just want a ratio. So that's what I'm saying. You can come up with a better idea sometimes. You should do that. Definitely should do that. Clear with this? So that is there. That is how you do when things are at an angle. Last thing, this is again completely not there in the portion for anything, but bits mein, CET mein, some random exams we can see. So we'll just put down a small formula for that. Doppler effect in light. Means when they used to ask a lot once in a while. Light ka formula is slightly different from the sound because there are a lot of things. The speed of light is different and blah, blah, blah. We'll directly write the formula there. This is just in case for different other exams. So the formula says the change in wavelength delta lambda is plus or minus lambda V source by C, or delta frequency is minus plus frequency V source by C. So use plus. Obviously, if the source is coming towards you, frequency would increase. Minus, if the source is going away, frequency will decrease. Here C is the speed of light. Since it is removed from the means, there is actually a better version of this. I don't think they'll ask you. Speed of light, and the best thing, this is independent of the observer. Let the observer run with any speed you want, it doesn't matter. Because light has a property, the speed of light in any frame is constant. So the C apparent ka formula valid nahi hoga, independent of velocity of the observer. So just let me give an example, how will they frame a question. So for wavelength, it is reverse. The sign will be reverse for wavelength, because when frequency increases, wavelength decreases. The question would be like this. So let's say we have a star. Star is going away with a speed of 10⁵ meters per second. In this process, it is emitting a wavelength of 6,000 angstroms. So you're sitting on the earth and you're watching the star. So the question is, what is the change in wavelength? Meaning, if the star is emitting 6,000, what do you see? Even then, China, meaning, let's say light has something weird property. Let's say there's a light wave which is going with speed C, and let's say there's one more light coming with C, and let's say you're sitting on this light wave. You will still think this light is coming with C. It's not 2C. So that is actually the first postulate of theory of relativity. Let's not get there. So in this formula, delta lambda, now see what is happening. Since the source is going away, the wavelength should increase. Frequency should decrease. Since the source goes away, lambda would increase, frequency would decrease. So apply the formula there. Lambda into V source by speed. So that would be 6,000 angstroms into 10⁵ by 3 into 10⁸. This thing comes out to be 2 angstroms, meaning this person will think the wavelength has become 6,002 angstroms. Bas, this is the kind of questions you will get. So you should know this much formula. Clear? But there's a pretty good concept on this. So that means if you have a star and if it is going away, observer is here. So he will see, if this is lambda, he will see lambda plus delta lambda, meaning the wavelengths will go more towards red. Wavelength increases. That is, the wavelengths will go more towards red. This is called redshift. Because red ka wavelength is more. This thing is called redshift. This happens a lot. So whenever you're observing astronomical objects, right, this is one of the issue actually with the telescope. You think the color of the star is some green, but in reality it is some other color. Same thing, if you're going with speed V this way, and if this was lambda, this person will see delta minus delta lambda. So here the wavelength decreases. So wavelengths are more close to blue. This is called blue shift. Means in an extreme case, think of like this. Let's say if you have some kind of a star or something, black hole or something there, and let's say there is a planet here, which is going in a circle. And if you're standing here and observing this, you will notice when this guy is going away, it looks more reddish. The wavelength will be lambda plus delta lambda. When that same thing is coming towards you here, it looks more bluish. It will be delta minus delta lambda. Meaning in an extreme case, that same planet will look red on the right side and blue on the left side. And now from here, you can measure both the change in wavelengths, isn't it? So from here, I know delta lambda in this thing. From here, I can find delta lambda is lambda into V source by C. From here, I can find the V source. That means I found the speed of the planet. I know the speed of the planet. I know the time of the planet. So then from there, I can get time period, because I know the time interval. It's almost half revolution. So time will be 2 pi r by bs. So from here, I got the radius. And since I already know the time period, so time period of a satellite from gravitation is given by 2 pi root over gm r power 3 by 2. From here, I can find the mass of the star. So using Doppler effect, you can find the mass of the star without actually going and measuring it. This is how you can find the mass of a star. Remember this formula from gravitation, where r is the radius of the orbit. Let me put smaller. So from the Doppler shift delta lambda, I can find the speed of the planet. And I know the time interval between the two things. So from there, I got the time. From there, I can find the radius. If I know the radius, I can find the mass of the star. You can relate questions like this. So Doppler, circular motion, gravitation. Clear with this? So you should just know this formula, nothing much. The formula in light and sound is a little different. And this formula, right, is valid only if the speed of the source is much, much less than speed of light. If it is comparable, relativity will come and the formula changes. That was completely removed from the portion, so we'll not even touch that. The only time I saw those questions being asked was in mains. No other exam never touches that part. They're happy with this much. Even in NCERT, they just stick to here only. But mains mein, those people are God. Last 3 years, they asked that question 2 times actually, when the speed of light is comparable and people got trapped. Anyways, now they won't ask, so we are safe. But anyways, this thing, like I said, whatever I taught you today is actually most of the things out of portion. But it's not difficult, right? It's only we're just playing with 1 or 2 formulas there. Okay, so with that, we'll wrap up for the day. So with that, we are done with waves on a string and sound waves. Friday, when we catch up, we'll start off with capacitors. We'll finish off capacitors, electricity, and then we will see what to do next. Either we can do wave optics or we can go ahead with magnetism. Wave optics is actually quite important. That's also a pretty high weightage topic. So wave optics and alternating current, and EMI. These 3 are just like rotation in mechanics. They have pretty good weightage and they're solid topics. Okay, we have done almost 53 questions. So please make sure to go through all of them and start solving. Don't delay, don't keep waiting, because you can see literally every 1.5 to 2 weeks you're finishing off a chapter. So you need to keep solving parallelly, and we'll not get time to revise all these things again during the revision. We'll be focusing more on the 11th ka topics. So do them properly. I know most of you are worried about the revision kya karna and all. See, you are just unnecessarily panicking and trying to think about revision. Sab theek hai, but what is the point of messing up the current chapters and then thinking of revision?